On units in advanced KS5 post-16 chemistry. So the first unit we'll come across is the mole, followed by grams per mole or grams per litre, grams per deciliter, grams per meter cubed, which is basically a fancy word, and it's known by the word molality, which is basically a fancy word for fluid density. And then you've got the very famous molarity, which is the concentration. And moles are measured in moles, and volumes measured in meter cubes, cm cubed, deciliter, liter, dm cubed, and the most popular is dl, deciliter cubed. And conversions would be a separate video. So molality would be density. This is density. So, and then you've got the rate. In reaction kinetics, you've got rate measurement, first order, pseudo order, second order, and the half-life of the reaction. So that's molarity divided by the time. So that's mole per dm cubed per seconds. So it's written as moles per dm cubed per seconds. So that's that, moles per dm cubed per seconds. So that's how it is. Right. And then once the rate equation, which is the rate equation is P1 plus P2, either a dynamic or a static equilibrium. In this case, we'll use it as a dynamic equilibrium, going back and forwards R1 plus R2. So that's that. And so our rate equation would be equilibria equals R1 R2 divided by P1 P2 Z prime. And then the equation would be, the units would be R equals K, A, and B. So that'll be the order of the equation, x plus y. So what we need to find out, that we know the rate is moles per dm cubed per seconds, but we need to find out what the units of the K are. So the units of K would be R divided by mole dm cubed per second squared, sorry. So that'll be, because it's moles per dm cubed per second times moles per dm cubed per second, so that it gets multiplied as mole squared, molality, so that's molality squared times squared. So that would be, in this case, the K's units would be a constant ratio. So basically, K would be dimensionally silent, because this cancels out either way. So in chemistry, you'll come across mole, which is mass divided by molecular mass, or atomic mass. Mass of a compound divided by molecular mass, and mass of an atom divided by its atomic mass. That's how it is. Depending on what you're using on top, the bottom will change, the denominator will change with respect to the numerator. So then you've got grams per mole, and that's the molality. The whole aspect is molality. Fluid density, then molarity, moles per dm cubed. The rate would be moles per dm cubed per second. And then the reaction, after the reaction equation that's been examined here, usually the units of rate would be mole squared per molality squared divided by time squared. So that would be like this. this one would be rate units. So that's pretty much it, to be honest. The rest is logging, log, units, and which is quite straightforward. So all you'll come across in advanced chemistry would be these units, and you'll have to rotate them over and over again repetitively. What else I was going to say? So we've got we have electrochemistry, in which you use equations like Ne, Q equals Ne. You use Q equals IT. You use you use electrical equations. You use Faraday's constant in electrochemistry. You also use in thermochemistry. You use P equals E over T, P equals IV, E equals IVT, or I squared R, or V squared over R T. So I squared R T, V squared, that's for heating. And then you use you also use E equals mc theta T, which is mass of the fluid times specific heat capacity of the fluid times the temperature differential. And you use E equals ml for latent energy, latent heat of fusion, and vaporization. So this is what you use for electrochemistry. And then so for electrochemistry, we've done that. For thermochemistry, we've also established the formulae we use. And then we've got colligative, and then the rest of the chemistry, which is physical and organic. We use the same units throughout the course. One of the other branches of chemistry would be atomic orbitals, which use quantum units. They use quantum units like the psi and the well probability distribution of an electron in the well, Schrodinger's equation, which is d d plus d y over dy plus d z over dz. And then we use atomic orbital equations for d orbital, which is dx squared minus y squared dz squared. So that's the SPDFG orbital configuration of orbitals. And so that's pretty much it, to be honest. All the way from atomic chemistry to organic chemistry, physical chemistry, industrial processes, colligative properties, thermochemistry, electrochemistry. We use the same units throughout. And once you master these, and you make a list of these, and you understand that it's N equals C times V everywhere, and C1 V1 over N1 equal C2 V2 over N2 everywhere, you wouldn't have a problem in plugging molar ratio formulaic substituents. So I'm glad we were able to cover this in the most informal way, and I hope you learned something, and I apologize for the slight mess here. It was a bit hard to control camera and the pen at the same time. The papers are loose. These are loose leaves, and it's quite hard to drag the pen over them because they tend to move and translocate as I write on them. That's pretty much it, and I hope you learnt something today. If you have any questions, please post them in the comment section below, and I'll try my best to answer it. Cheers, bye now.